Hi, this is Bartosz Miluski, and this is the first installment in the series of tutorials about C++11 and concurrency. What prompted this series is the new C++11 standard, which has just been ratified, and it comes with threading support, a portable support for threads. So that it has thread, mutex, condition variable, futures, package tasks, and stuff like this. It also comes with a memory model, which essentially describes the visibility of writes between threads. And there is a library, atomic library based on this memory model, which contains atomic variables and fences. The standard also comes with a lot of other interesting things like lambdas, move semantics, which I will be using in this tutorial, and I'll be explaining these things as well. This is a fully hands-on tutorial, so I will often be writing code, editing it, compiling, running, and sometimes even debugging. Let me say a few words about compilers. This is a new C++ standard, so the support for it is very patchy. There is one compiler on Linux, GCC 4.7, which has the best support. I'll be mostly using Visual Studio 2010. Doesn't support threads, standard threads, but there is a library I'll be using by Anthony Williams, Just Thread. It's the most complete implementation of the standard that I know of. There are other libraries. These two libraries are task-based, which is a very interesting approach to concurrency, which I'll be discussing too. If you're into books, Anthony Williams wrote a very nice book about this new C++ standard as far as concurrency is concerned. There is this book, Parallel Programming with Microsoft C++, which introduces a lot of concepts about parallel programming that are generally applicable. If you are into theory, then The Art of Multiprocessor Programming is a very good book. Debugging is very difficult. Our company, Concurrency, makes Jinx, which is bug accelerator. But if you can't afford it, there are other free offerings on the market. This is Hello Thread. We'll start with the simplest possible program traditionally, and I'll show it how it works on Linux using GCC 4.7 and then on Visual Studio using the Just Thread library. Here we are on Linux. I have GCC version 4.7 installed on this machine. And let's start writing our program. I'll call it thread.cpp using the trusty old VI. So we want to write a program that will create a thread, and in this thread it will print hello thread. In order to print something, of course, we have to include IOStream. Okay, and since we want to create a thread, include thread, obviously. Let me go to main immediately, int main. And the first thing we want to do is create a thread. And that means just declaring a thread object, std thread, and constructing it. I'll call it th. And what you pass to the constructor of a thread is a function. So this thread will execute the function and then exit. I don't have a function yet, but I'll write it later. Let's call it thread function. Okay, so the thread is now created. It will be nice to actually print something from main so that we know that we have two threads. One is the main thread, and the other is our worker thread. So let's write hello world, exclamation, new line. Okay, now if I finished here and closed the brace, what would happen is that a thread would be created indeed, then main would print hello world, and then it would exit immediately. That's the end of main. And it's very unlikely that the thread would actually start because it doesn't have the time to do that. Right? So we have to wait for the thread to finish. We have to wait until the worker thread has done its printing. And this is done by calling the threads method join. Okay, and just to satisfy the compiler, I'll say return 0 because we are successful. Okay, what's missing is the thread function. So let me write the thread function. Void thread function. It could also take arguments, but in this case we won't pass any arguments. Maybe in the next installment. std_cout, and here's our famous printout. Hello from thread. Oh, new line. And that's it. That's the whole program. We have included thread because we're creating threads. We have a thread function that does very little. And we have main, in which we create a thread, passing it a thread function. We print something, and then we wait for this thread to finish. While we are waiting, we are idle. Nothing is happening in the program, and actually the operating system can take the processor away from us and do something else. So let me save this. I have a makefile here, so I will just compile it very quickly. Okay, no problems. And let's run it. And indeed, main printed hello world and thread printed hello from thread. So that worked. The simple example that I've shown you, the hello thread, is an illustration of a more general idea of fork join parallelism. This is a very popular pattern that's used in concurrent programming. And this is an illustration that shows it. You start with a single thread. Time here goes from top to bottom. You hit a fork, at which time the execution splits into two branches. One is the continuation of main, in which we print hi from main and then call join. And the other branch is the worker thread that prints hi from thread and finishes, and then they both join and continue as a single thread. So this is an idealistic picture. In reality, things are not that symmetric. Here's a more realistic picture. Again, we start with single thread, and we call the constructor of thread. So this is our fork point. And while the worker thread is starting, which takes usually a long time, because there is a big thread creation overhead in the operating system. Okay, there are ways of dealing with this, like thread pools and so on, which I'll talk about at some other point. So while this thread is being created, main continues and prints hi from main and calls thread join, and this call blocks. And for this duration, the thread is blocked. Finally, the worker thread gets a chance to run, and it prints hi from thread and finishes, and at that point the main thread is unblocked, returns from the call to join, and continues single-threaded. So you don't really see a lot of parallelism in this particular program, and you usually see hi from main followed by hi from thread almost every single time. Here we are in Visual Studio. This is Visual Studio with the library JustThread that implements threading support. And as you can see, I just rewrote the same program, hi from thread, hi from main. What I want to show here is the debugging. Okay, the traditional debugging in Visual Studio. I'm going to set a breakpoint inside thread function, and I'll set another breakpoint at the end of the program. And we will stop in the thread function, and I'll show you the thread display. So let's start. Okay, here we are in thread function. Now what Visual Studio has is this nice display of called parallel stacks, which displays the threads. So we do have two threads. This is the main thread, and you can see main, and I can double click on it and it shows me where we are in main. What actually happens is inside of main we are calling operator left shift, so we are already printing, and operator left shift calls a whole bunch of library functions ending up in kernel 32. In the meanwhile, thread 1, one thread is inside thread function. This is where we stopped. And you can see that thread function was called from some startup routines, starting with thread start ex. So if I continue, we'll get the printouts, and here's what happens. Hi from main, hi from thread. As I said, the fork join is really not that symmetric, so main has the opportunity to run first before the worker thread gets its own opportunity. Let us play a little bit with this program. I would like to demonstrate the use of lambdas, because this is the thread function here is tiny, right? I would like to, instead of calling the thread function right here, I would like to define this function on the spot, and that's called a lambda from lambda calculus. And the symbol for an inline anonymous function, a lambda, in C++11 is the bracket, open close bracket. Treat this as a symbol, as like a Greek letter lambda. Okay, and now the definition of a function follows. So it starts with the argument list in parentheses. Well, in our case, there are no arguments. Now, the body of function, I will just take this here and copy it right here. And I will format it appropriately, because this is the usual formatting that people use with lambdas. So it's good to get used to it. Notice that the closing thing, that's this funny combination of symbols that's very characteristic for lambdas, because it closes the brace, the body of the function, and then closes the parentheses because the function is passed to some other function, right? And the semicolon. So this graph sort of shows you that this is the end of lambda. So that's it. And now I can remove this and compile. right? Let's see. Did I make any mistakes? No. Of course, I can run it, right? And as before, it prints high from main, high from thread, except that now the function is defined inline. And this is an interesting way of looking at parallelism, that you create a block of code that is being executed sort of out of time. And so you just say, do this in parallel, do this code in parallel, and then continue while this code is executing, and let's say call print high from main, and then join and wait until whatever you spawned finishes. This is very reminiscent of task-based programming. This is sort of in between thread-based programming and task-based programming. Okay, now what I want to do is to show you a more interesting example of parallelism. So this is fork and join, except that now we are forking in more directions. We have more branches. The schematic for this is, you start with one thread, you fork into several branches, and then you join them. But this time you are joining not one thread, but many threads at the same time. So this is called a barrier, usually, or thread barrier, where you actually put a barrier and all the threads will stop and join at this point. Now, there is no direct support for barriers in C++11. However, we can simply write one for ourselves. So first of all, we want to write a for loop, right? For int I equals 0, I less than, what should we say? Let's say 10. 10 threads, fine. Plus plus I. We'll open this, close, do the indent. Okay, so we are starting 10 threads. And then we are going back to main. Okay, but what do we do with these threads? Now we have to wait for these threads to finish, right? So we have to store in some way the results of thread creation, right? So we'll have a standard vector of std thread. So we have a vector of thread objects. Let's call it workers. Okay, and now every time we create a thread, we'll push it back on this vector. Workers push back. Okay, push back standard thread of this lambda, right? And I have to close one more parenthesis. Okay, so we have a vector of workers, and then we push back new threads onto this vector. And we are constructing a thread and passing it a lambda. Oops, I don't want to move this. Okay. So now all these thread objects are sitting in the vector, and we have to join all of them. So since there is no barrier, we'll just have to join every single thread in a loop. And I want to do it with for each, because I don't like using these iterators directly. And this is, after all, C++11. Okay, for each is defined in include algorithm. Algorithm, correct. Yeah. And for each takes 3 arguments. The first argument is the beginning iterator. So this will be workers begin. The second argument is the end iterator, workers end. And, the nice thing about this is that I don't have to write anywhere what the type of the iterator is. And finally, I want to pass a function that will be executed on every element in the vector. In this case, I will join, right? And I just want to write this function inline because it doesn't do much, right? So I'll use a lambda symbol. Now this lambda takes an argument, and this argument is the element of the vector, and the element of the vector is std thread, and I'll call it, let's pass it by reference, th. Okay, and now the body of the lambda. Just th join. Okay, the end of the body. And now I have to close the parentheses. Right, so this parentheses and this. Okay, let's look at this program. Does it look okay? It looks okay to me. So let's compile. Yes, excellent. It worked. Now let's run this program and you'll see what it produces. Okay, here's the result. So this is an interesting thing that happens. What we are seeing is actually an actual interleaving of threads. So while we are in this loop starting threads, some of them have already started. So we have the first hi from thread here, hi from thread, and this is probably the end of the loop, and then we print hi from main. And then the other threads that we just started in this loop, they get their chance to print hi from thread. Let me run this program again. So here you see after 2 threads, hi from main. Okay, let's try again. This time, after 1 thread, there is hi from main. So the result is different. And this is very characteristic of concurrent programs, that they are not deterministic. Every time you run them, you might get a different result. And the fact is, we don't really like that. We try to write concurrent programs in such a way that they give the same results every time we run. Because dealing with programs that are not deterministic is really hard. Let me do one more thing just for fun. Here we have the printout from every thread that says the same thing, hi from thread. So we don't know which thread is printing what. But we have an index here, right? If we could print this index from the thread, we would know which thread is doing what. So let me just try it. Okay, space. And here we print I, like this. Now you can see that there is some complaint from the compiler that it does not see I. And that's because the body of lambda doesn't have access to variables that are defined outside of this body. However, there is a way to actually tell the lambda, hey, capture this variable. So if I put I in between these brackets, it means capture variable I and actually capture it by value. So at this moment, it will copy it and will store it inside a function object. Because a lambda is really a function object, and this function object can have private data, and the copy of I will become private data of this object. And this whole thing is called a closure. A closure is a lambda that captures external variables. So let me compile this program and run it, and we'll see what happens. And this better be interesting. Okay, here it is. Oh, now there is more interleaving. Not only there is interleaving between the printouts, but there is also interleaving inside printouts. That's because the printout is now split into high from thread, and then there's separate call to print I, and there's a separate call to print the exclamation mark and new line. So this thread can be just preempted in the middle, and some other thread can run. So let's analyze what happened here. High from thread, nothing. High from main. Okay, so we already finished the whole loop, and we are in main. Now the other threads are starting. High from thread, nothing. So the number hasn't been printed for these two threads. And then high from thread 2, high from thread 3, and now high from thread 9 suddenly. So they are coming here out of order. And now we have this 1. Okay, this 1 was probably from one of these two that didn't print the number, because they were preempted in the middle of the printout, right? And there is a 0 at the end that was from the first one that was able to print anything. Now, let me try to do this again, just to see that the result is different every single time. Okay, here we have 0, 4, 5, 3, 8, 2, 7, 1, 6, 9, and finally main. Yet another completely different execution. So that shows the non-determinism in concurrent programs very clearly.